In this section, we're going to look at divergence and curl in three-dimensional space. So the last sections of this chapter, the focus is going to switch to two-dimensional space using Green's theorem to a three-dimensional space. When we talk about divergence, that's just a measure of the expansion or contraction at a single point. So when we measure divergence, and that doesn't matter if we're in two-dimensional space, or in this case, we're looking at three-dimensional space, it's simply going to be a scalar. If it's positive, it's an outward expansion. If it's negative, it's an inward contraction. If it's zero, there is no expansion or contraction. Previously, we had talked about divergence in two-dimensional space as the partial of f with respect to x plus the partial of g with respect to y. But now that we're in three-dimensional space and our vector field FGH, then when we compute our divergence, it's going to be the same, partial of f with respect to x plus g with respect to y plus h with respect to z. Now this is a dot product, which is why this is going to be a scalar, because dot products are scalars. And it's going to be the dot of our vector field with this symbol, which is what we call the del operator. When we talk about the del operator is simply the vector where it's the partial derivative with respect to x, y, and z. So if we take that vector and we dot it with our vector field, then we get that dot product inside the box. So just remember that if divergence is zero, our vector field is source free, so we don't get an expansion or a contraction at that point. In example 1, we're going to compute the divergence for this vector field. So the divergence of our vector field is simply going to be the dot product that's going to give us, and I'll write this out once and then I won't write it out anymore. The partial with respect to x dotted with the partial derivative with respect to y and the partial derivative with respect to z. So we're going to dot that with our vector 2y plus z, x minus z, x plus y. And that dot product is going to be taking the partial derivative with respect to x of the first component, which is 2y plus z, plus the partial derivative with respect to y of the second component, x minus z, plus the partial derivative with respect to z of the last component, x plus y. You can see when we take these partial derivatives, it's just going to be 0 plus 0 plus 0. Our divergence in this particular example is 0, which means it's source free. Let's try another. In example 2, we need to find the divergence for this vector field, and I'm not going to write it all out like I did before. I'm just going to simply compute the divergence by looking at the first component and taking the partial derivative with respect to x, so it would be a negative 2, plus second component partial derivative with respect to y would be a negative 1, plus last component, take the partial with respect to z, and it's 1, which gives me negative 3 plus 1, or negative 2. We have a negative flux. That means the flux is going to be inward, although it didn't ask for this. We have an inward flux. So remember, that's also called a sink. This represents a contraction at the point. This next example, we're using this vector field that happens to be a radial vector field, and it's of a specific form. But first, what I want to do, because I have to find partial derivatives, I'm going to rewrite this vector field as the vector x times x squared plus y squared plus z squared to the -1/2, and then I'll do the y times the same expression. It'll just be easier when we do our partial derivatives. And the last component, z times the same expression. Okay, so this is a pretty long expression. I don't want to do the partial derivatives of all of these on one line. So what I'm going to do is first compute the partial derivative of f with respect to x. So recall the first component, that's our f, second is g, third is h. When I compute the partial derivatives, I have to use the product rule. So I'm going to do derivative on x, keep the x squared plus y squared plus z squared, plus keep the x, and then the derivative of the second expression, which would give me x squared plus y squared plus z squared to the -1/2 plus x times -1/2 times x squared plus y squared plus z squared to the -3/2 times the derivative of the inside with respect to x, which would be 2x. Now I'm going to skip a lot of the algebra steps, but when I simplified this, I got down to y squared plus z squared. Notice there's no x in the numerator. The denominator is x squared plus y squared plus z squared to the +3/2. Similarly, when I compute g with respect to y, I have the same denominator. The numerator will be missing the y, so it'll simply be x squared plus z squared over the same denominator. So you can verify this. And then h with respect to z will be missing the z in the numerator. It'll be x squared plus y squared over, I'm ignoring that phone call, x squared plus y squared plus z squared to the 3/2. Remember, when we compute our divergence, we are going to be adding f with respect to x plus g with respect to y plus h with respect to z. When we add those all up, luckily they have the same denominator. What we get is 2x squared plus 2y squared plus 2z squared over the denominator x squared plus y squared plus z squared to the 3/2. Now notice if I were to factor out the 2 in the numerator, I would have in parentheses x squared plus y squared plus z squared, which is the same expression in the denominator. So we can further reduce this to 2 over the square root of x squared plus y squared plus z squared. And that's going to be the divergence. So what I would like to do is go back to our vector field. And I am going to let a vector r be equal to the numerator x, y, z of our vector field. Notice that the magnitude of this vector is going to be the denominator of our vector field, which is the square root of x squared plus y squared plus z squared, which means our vector field can be written as this vector r over its magnitude. The divergence in this particular case ended up to be 2 over the magnitude of r, but I'm going to go ahead and write 2 as 3 minus 1. And there's a reason that I'm doing this. And it has to do with this theorem 16.8 below. But whenever you're computing divergence and you have this radial vector field, just a regular radial vector field, you don't have to do all the algebra I just did. You can use this theorem that says if you can write a vector field in this form, where the numerator is this vector r, which is x, y, z, and the denominator is going to be the magnitude of r to some power p. So notice that p is the numerator of the exponent over 2. In our case, going back to what we had, our p-value, oops, always do that, our p-value is equal to 1. Which is why when we computed the divergence, it's always going to be 3 minus p, and in our case p was 1, so I did 3 minus 1, over the magnitude of r to the power of p, and in our case our p was 1. So again, if you have a vector field of this form, then you can use this theorem to compute the divergence. You don't have to go ahead and do all those partial derivatives. When we talk about curl, we're talking about spin at a point or rotation at a point. So when we're looking at curl in three-dimensional space, that spin is unlike divergence, which is just simply inward outward. So a positive negative can accurately describe divergence. Not so with curl, because the direction in which it spins, there could be infinitely many directions in three-dimensional space, which is why when we compute curl in three-dimensional space, it's going to be a cross product. It's going to remain a vector so that we can accurately describe the direction that it's rotating or spinning in. So where divergence is a dot product with the del operator, curl is going to be a cross product with the del operator. So now in this box, they've just computed the cross product, but notice that there's usually when we do this, it's going to be a plus minus plus. Notice that the second term, the j term, has a plus, not a minus. And that's because the order of partial of f with respect to z minus partial of h with respect to x, if you reverse that order, then you'll get the minus on the outside. I prefer just to compute it as I always do with a plus minus plus. So again, just a reminder that if curl is 0, then it's irrotational, meaning there's no rotation. In example 4, we're going to compute the curl for our vector field x squared 2z y. So the curl of our vector field is simply, and here I'm going to use I, j, k. Remember, del operator goes first, so partial with respect to x, partial derivative with respect to y, partial derivative with respect to z, and then I have an x squared 2z y. Computing this, and I'll write it all out like I did with the very first example with divergence. Remember, you ignore the I column and you're just looking at the cross for the last two, so multiply minus multiply. This is going to be the partial derivative with respect to y of y minus the partial derivative with respect to z of 2z, and that would be my I component. And I do the minus. I don't use what's in the box because it's just easier for me to do what I've always done. Looking at covering the j column, it would be the partial derivative with respect to x of y minus the partial derivative with respect to z of x squared. That's my j. And then it's a plus partial derivative with respect to x of 2z minus the partial derivative with respect to y of x squared. Which is my k. Let's see, this would be 1 minus 2i minus 0, j plus, and it looks like it's going to be 0 for k as well. So you could simply write this as negative I, or you could write it in component form as -1, 0, 0. So what does this mean? Well, notice that the first component is a constant number, -1, but the last two components, which would represent the y and the z, those are 0. So although this is not asked for in the problem, if I were to interpret this, I would have a constant rotation. Now remember, when we're talking about rotation, if it's positive, it's counterclockwise. If it's negative, it's clockwise. So this is a clockwise rotation. And it's going to be in the x direction. And there's no y or z value. So that's how you would interpret this answer. In this next example, we're going to go ahead and graph our vector field, but we're just going to graph it in the xy plane. And then we're going to compute curl. So when we compute the curl, it's going to be for the whole vector field, x, y, and z, but we're just going to graph in the xy plane. So since my vector field is 0, negative x squared, 0, and this would be my xyz or fgh. If I were to just look at graphing the vector field in the xy plane, I would look at 0, negative x squared. So since we're only in the xy plane, let's just get some points. Notice that if I'm at the origin, at the point 0, 0, that's going to correspond to the vector 0, 0. So it's just the point. And in fact, notice that when my x value is 0, so that would be any point on the y-axis, the vector will always be the 0 vector. So if I pick any point on the y-axis, I have no vector, essentially. So let's try something else. Let's look at the point 1, 0. At the point 1, 0, that would correspond to the vector 0, -1. So this would just simply be a downward vector. At the point 2, 0, that's going to correspond to the point 0, -4. So at 2, 0, we go down 1, 2, 3, 4. And if you can see at the point 3, 0, it's going to correspond to the vector 0, -9. And it doesn't really matter if I have positive x values or negative x values. So if I had -1, 0, it would still correspond to the vector 0, -1. So it's still going to go down 1. And that's true if I had the point -2, 0. It's going to go down 1, 2, 3, 4. And in fact, if I pick any point where my x value is 1, doesn't matter what my y value is. So let's say that we're looking at 1, 3. It's still going to go down 1. Or -2, 4, still going to go down 1. And pretty much, let's see, at 3 it would go 1, 2, 3, 4, 6, 7, 8, probably something like that. So that's pretty much what our vector field would look like. You can go ahead and, oops, made an error here. At -2, 4, it goes all the way, sorry. So you can go ahead and just sketch a few more just so that we can get an idea of what this vector field looks like. And that's sufficient. So now when we compute the curl of our vector field, we're going to look at all three components, right? Your I, your J, and your K. We've got crazy roosters today. So this is going to be the partial derivative with respect to x, y, and z. Our vector field is 0, -x squared, 0. I guess I didn't need all this space up here. I'm just going to eyeball this. Partial derivative of z with respect to -x squared would be 0. So this is going to be 0i minus, when I do j, it's 0 minus 0, so 0j. And when I do k, it's going to be -2x minus 0, so -2xk. And my curl is -2xk, or you could write it as the vector 0, 0, -2x. So notice that this is not constant. We have that variable x. So again, although the problem didn't ask us to do that, let's see how we can describe the curl. Well, first of all, the rotation is in the z direction because I only have a z component. Now, if you had more than 2, or even if you had 3 components that had constants or variables in there, then you could say that you could describe the rotation with respect to each variable. So since it's a -2x on the z component, I could say I have a rotation in the z direction. If I had some non-zero number in the x slot, I could say I have a rotation in the xz, right? If it's all 3, you just have a rotation in the 3-dimensional space, and you would have to describe each piece. So this is a rotation in the z direction. I can't say that it's clockwise even though there's a -2 because of the variable x. Remember, x can be anything. If x is negative, this turns out to be actually a positive z value. If x is positive, it's a negative z value. So the rotation is in the z direction. However, I can specifically state that if the x values are positive or greater than 0, then that component would be negative, so it's going to be clockwise. So rotation is clockwise. If x is negative, then our rotation is counterclockwise. Because it will be positive. And then if x is equal to 0, there's no rotation. So When we talked about divergence with respect to a radial vector field, remember radial vector field are vector fields that are like outward or inward from the origin. And divergence is the measurement of outward or inward movement at a point. So they go together. And we had that special property with radial vector fields. Well, when we talk about curl, it's this idea of spinning or rotation. So we're going to have some nice properties when you have curl, when you measure curl, and your vector field is a rotation vector field. So our rotation vector fields, those are vector fields that spin either clockwise or counterclockwise. So they're either going to go with the curl or against the curl. There's going to be some really nice properties. If you do have a vector field that is rotational, then you will be able to break it down into a cross product of some constant vector A crossed with vector R. Now, vector R is the exact same vector we had previously when we talked about radial vector fields. R is simply the vector XYZ. If you can take your vector field and break it up into some constant vector A, and here this is a non-zero constant vector. One of the components can be zero, but not all of the components can be zero. So A is going to look like A sub 1, A sub 2, A sub 3, where not all of those A's are zero. Okay. So for all non-zero choices of our vector A, this nice property is that the magnitude of the curl is going to be 2 times the magnitude of A. And now if it is a rotation vector field, and you're talking about curl, then it makes sense that if you're looking at divergence in a rotation vector field, that it would have to be zero, which is why when you take the dot product of the del operator with the vector field, which is simply divergence, it will necessarily be zero. So what's nice about this is if you do have this situation, then you can also get your angular speed. Angular speed, so we use the lowercase omega, Greek letter, for angular speed, is simply going to be the magnitude of your vector A, which would be half of the magnitude of the curl. And just as a reminder, the angular speed is a rate. In this particular case, it's in radians, not degrees. So this speed will always be in radians. If you want degrees, you can convert it. We're just going to verify a few of the properties in this box. We're not going to verify angular speed. That's given information, but we'll verify a bunch of the other stuff. So what we're going to do is we're going to look at this particular A, which is the vector 1, negative 1, 1. And then R will be XYZ. So A is a constant vector. R is our vector XYZ. Their cross product will give me a rotation vector field. Here's the diagram. This is the idea of what's going on. When you do find this vector A, the nice property is that it's going to be going in the same direction as your curl. So in this diagram, our curl is this long blue pink vector. Notice that if I did cut the length of this curl vector in half, I get the length of my vector A. So it looks like the magnitude or the length of the curl vector is actually equal to twice the magnitude of A, but we'll verify that. So that's a nice thing about this constant A. It's going to go in the direction of the curl, and then it has all these really nice properties. So the first thing I'm going to do is I'm going to compute the dot product. And oops, I'm going to find my vector field, which would be A cross R. I have my I, my J, my K. A is 1, negative 1, 1. R is X, Y, and Z. I have negative z minus y, that's my I, minus z minus x, j, plus y plus x, k. If I were to clean this up, it looks, oops, it's always doing this. I have negative z minus yi minus, or maybe I'll do the plus and change the order, distribute that negative. So plus x minus z j plus y plus x k, or written with components, which is usually what I prefer. I get this following vector field. So this resulting vector field is a rotation vector field because it is the cross product of a constant non-zero vector A with R. What I'd like to do now is compute the curl. When I compute the curl, it's going to be partial derivative with respect to x, y, and z with my vector field negative z minus y, x minus z, y plus x, or x plus y. That will give me 1 plus 1i, so 2i, minus 1 plus 1, so minus 2j, plus 1 plus 1, so plus 2k. Look at this cross, which is our curl. If you factor out the 2, the vector left over is I minus j plus k, or 1 minus 1, 1. And that's simply 2 times the vector A. So the cross product, or the curl, is equal to 2A, which means that if you take the magnitude of the curl, it's going to be equal to the magnitude of 2 times our vector A, which is simply 2 times the magnitude of A. So verify that property. And also note that since this is a rotation vector field, if you take the dot of the del operator with your vector field, it's going to be the partial derivative with respect to x of the first component, which was negative z minus y, plus partial with respect to y of our second component, x minus z, plus partial derivative with respect to z of y plus x. And that's just going to be 0 plus 0 plus 0. So that's 0. So I've just verified that the dot product is 0 and the magnitude of the cross product is 2 times the magnitude of A. I've also verified that I can come up with a rotation vector field by taking any non-zero vector A and dotting it with our vector R so that it fits all of those properties. So now that we've verified those properties, and we're not going to verify the angular speed, that's just given information, then you are free to use whatever is in that box. On this last page, these are just some properties and the theorems that you're free to use. You may or may not use them. Looking at divergence, remember that's a dot product. So if you are adding two vector fields for some reason and you're trying to figure out the divergence, you take the del operator and you can dot it with, you can either add the vectors first, or you can do the dot products first and then add them. So that del operator, that dot product will distribute. And if you have a constant times your vector field, you can either do that first and then dot it with the del operator, or you can pull the constant out and do the dot product first. So these are just some properties when you're computing divergence and curl. So if you have curl, remember that's a cross product. So there's some similar properties. You can either add the two vectors first and then cross with the del operator, or you can distribute that del operator and do the cross product with each vector field and then add them. And then we have the constant multiple of our vector field. You could do that first and then cross it with your del operator, or you can pull the constant out, do the cross product first. Okay, so you're free to use those properties. Then here's a nice theorem. The curl of a conservative vector field. So let's say that the vector field is conservative. Going back to our properties, remember we had these properties that we had to check. And if it's conservative, then we're going to let the vector field be some gradient vector field for some function phi, where phi is our potential function. Then the cross product of the del operator with our vector field, which is our curl, is going to equal to the cross product with the gradient field of the potential function, which makes sense, and that's going to be the zero vector. So the curl of the gradient is a zero vector, and f is going to be irrotational, so no rotation. And here's another theorem that may come up, or you may use it. Let's say you do have a vector field, and you're going to take our del operator, you're going to dot it with the curl, and that's equal to 0. That just means the divergence of a curl is 0. That makes sense. Okay. We also have what's called a product rule for the divergence. So let's say that you have u, it's just going to be a scalar valued function. So it's just a function. Okay. It's scalar value because it's not written as a vector, that's all. So any function. So if you take this function and you multiply it by your vector field and then you dot it with the del operator, then similar to that previous property, you can go ahead and do this weird distribution where you take the del operator of the function dotted with the vector field, you're going to add it to the function times the dot product of the del operator with the vector field. That's similar to the product rule when you're taking derivatives. So it kind of looks like that. And then let's just say that you do have a conservative vector field. Then there's these properties that are all equivalent. Well, if it's conservative, you know that you're going to have a potential function phi, so that the vector field is equal to the gradient of phi. So this is just extending all of our properties to this three-dimensional space. When you take our line integral that we had previously, you can use a fundamental theorem saying this is going to be phi of b minus phi of a. And then if the line integral happens to be 0, or I'm sorry, since it's a conservative vector field, the line integral will be 0. And then the curl is going to be 0. So again, this is just restating properties of conservative vector fields in respect to this idea of curl in three-dimensional space. So that's it for this section. It's not a very long section.